Chapter 21 is all about the normal distribution and all the different pieces that go along with it. So let's look at the opening problem. A salmon breeder is interested in the distribution of the weight of female adult salmon. We'll call that W. He catches hundreds of female adult fish and records their weights in a frequency table with class intervals with weights between 3 and 3.1 kilograms, 3.1 and 3.2, and so forth. So if the mean weight is 4.73 kilograms and the standard deviation is 0.53 kilograms, these are the things to think about. Which of these graphs do you think is the most likely distribution for the weights? Is it perfectly, and where the weight is measured along the X and the frequency along the Y? This is perfectly aligned, kind of up and down, or bell-shaped. So this opening problem is showing us kind of how we can use information like this to create graphs, use mean standard deviation, and so forth. So one thing I want you to think about, read this paragraph. In the previous chapter, we looked at discrete, exact random variables and examined binomial probability, where the random variable X could take on non-negative integer values such as 0, 1, 2, 3, 4, up to n. So last chapter, chapter 20, was all about discrete or exact values that X could take on. 21 is more about a continuous random variable X, where X can take on any real value within some reasonable domain. There are infinitely many values X can take on, and even if a measuring device enabled us to measure X exactly, the measurements of X from any two members would never be identical. What this means is the probability that X is exactly equal to something is 0. So go ahead and write this down. For a continuous variable X, the probability that the random variable X equals an exact value X is 0 for every X. So for a continuous variable X, we can only talk about the probability measured value lies in an interval. So if you recall, discrete is always an exact value, things you can count, where a continuous variable is an interval like weight or measurement. All right, so since P, the probability random variable X equals an exact value X equals 0 for all X, we cannot use a probability mass function to describe the distribution. Instead, we use a density function or a distribution curve. All right, so go ahead and get this stuff copied, and through the next few days, we're going to kind of unravel this whole thing. Go ahead and pause the video. So lesson A is pretty straightforward. It's really just an introduction to the normal distribution. So you've probably seen this curve before. We can call this symmetrical because in the middle, it's symmetrical in the middle there, bell-shaped. But the big idea behind this curve is that it's a normal distribution. So this is our normal curve, and we will use that for this entire chapter. Go too far. All right, so anytime we're looking at measurements, we're going to be talking about this normal curve. So for example, consider apples harvested from an apple orchard. They do not all have the same weight. The variation may be due to genetic factors, the soil, the amount of sunlight, blah, 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 right? So anything that's being measured that can't have an exact value every single time, these are quantities that might be normally distributed or approximately normally distributed. Heights, lengths, yields of corn, volumes of liquid, weights of peaches, lifetime of batteries. All of these things that can be measured, we're going to use the normal curve. All right. So let's go ahead and get this part. When you draw the normal curve, first of all, the mean is the highest point. And one thing to recognize in a normal curve, your centers are always equal. The mode equals the mean equals the median. When all of these are equal, that's when you know that's a normal curve. All right. So just kind of the highest point here means that's the mode, that's where the mean is, everything. All right. So it's always symmetrical about the mean. Now, standard deviation. So notice in this curve, and I never do this right, so I just kind of draw the curve. But one standard deviation away from the mean occurs, the first standard deviation occurs at the point of inflection. So where it changes concavity. See how this is curved up and this is curved down? That's your point of inflection we talked about in the calculus unit. But in a normal curve, when we do our standard deviation, they always talk about there is about 68% of all data should lie within one standard deviation of the mean. Then you can go 2 standard deviations and 3 standard deviations. 99.5 maybe percent of all data lies within 3 standard deviations, and they say that all data should lie within 4 standard deviations of the mean. And that's 21A.